Before you close your eyes tonight, there is something you need to know about a star. Not a distant star. Not a star you have never heard of. A star you have seen. A star your grandparents saw. A star that every civilization in the history of our species has looked up at and wondered about. Its name is Betelgeuse, the red shoulder of Orion, one of the brightest stars in the night sky. And in July 2025, for the first time in the history of astronomy, after a century of suspicion, and after decades of failed searches, after every major telescope on Earth and in space had tried and failed to confirm what the data kept hinting at, scientists found something hiding inside it, not around it, inside it. A second star, small, dense, invisible to every telescope that had ever looked, buried so deep inside Betelgeuse's atmosphere that its light was completely swallowed by the red giant around it. They called it Siwarha, her bracelet, named after the Arabic meaning of Betelgeuse itself, the hand of al-Jawza. And 6 months after that discovery, in January 2026, the Hubble Space Telescope found something else. A trail, a wake of dense, hot gas, carved through Betelgeuse's atmosphere like the wake of a boat through still water. Direct, visible, undeniable evidence that Siwarha is not just orbiting Betelgeuse. It is ploughing through it, carving through the body of a dying star, dragging gas and dust behind it as it goes. And here is what nobody is saying loudly enough yet. Siwarha is getting closer. Every orbit, every 6 years, the drag of Betelgeuse's atmosphere slows Siwarha down. And when an orbiting object slows down, it does not fly away. It falls inward, closer to the core, deeper into the body of the giant. This is not going to end well for either star. And tonight, right now, as the world outside goes quiet, we are going to go all the way in, into the atmosphere of a dying red supergiant, then into the wake of a hidden companion, into one of the greatest astronomical detective stories ever told. But before we go there, before we descend into the body of a star that is slowly consuming its own sibling, I want to take you somewhere else first. I want to take you back, to the very beginning, to the first time a human being looked at this star and gave it a name. Welcome to Science for Sleep, the place where the universe slows down. If you are here for the first time, I'm glad you found this. Stay as long as you like. And if Science for Sleep has become part of your nights, if these journeys have kept you company in the quiet hours, a like on this video and a subscription costs you nothing and means everything. It tells the universe that slow, careful, science-rooted storytelling still has a place here. The subscribe button is just below this video. It will take you 2 seconds and then we can go. Tonight's journey begins with a star that has been watching us for as long as we have been watching it. Let us go. There is a constellation that almost every human being on Earth can recognize. Even people who know nothing about astronomy, who have never owned a telescope, who have never read a single book about the stars can usually find it. 3 bright stars in a row, evenly spaced, forming a belt. And around that belt, 4 more stars outlining the shape of a figure, a hunter, a broad-shouldered, standing tall against the winter sky. His name in the Western tradition is Orion, and he has been there, in that same patch of sky, for every civilization that ever existed. The ancient Egyptians saw him and associated him with Osiris, the god of the afterlife. The Babylonians saw him and called him the true shepherd of the sky. The Greeks told the story of a great hunter placed among the stars by Zeus himself. So the Hindu tradition saw the figure as the creator god Prajapati. Aboriginal Australians, who have one of the oldest continuous astronomical traditions on Earth, saw the 3 belt stars as 3 fishermen in a canoe. And in Arab astronomy, the constellation was associated with a female figure called al-Jawza, a figure of power and mystery. On the left shoulder of that figure, on the upper left corner of the constellation as seen from the northern hemisphere, there is a star that looks different from every other star around it. While most stars in Orion appear blue-white, this one is unmistakably red. Not faintly red, not ambiguously red. Visibly, distinctly, obviously red-orange. Even to the naked eye, even without a telescope, you can see the colour. It glows like a coal. That star is Betelgeuse. The name comes from the Arabic phrase Yad al-Jawza, the hand of al-Jawza. Over centuries of translation and mistranslation, As from Arabic to medieval Latin to modern European languages, Yad al-Jawza became Betelgeuse, the hand of the central one, the hand of the powerful figure. And for thousands of years, that is all anyone knew about it. A red star, a bright star, a star that marked the shoulder of a hunter in the sky. But there is a reason Betelgeuse is red, and once you understand that reason, the star becomes something much more than a point of light in a constellation. It becomes a story. And a story about birth and death and the terrible, beautiful physics of what happens to a star when it begins to die. Betelgeuse is red because it is enormous. Not enormous in the way that Jupiter is enormous compared to Earth. Enormous in a way that defies any useful comparison. If you place Betelgeuse where our Sun is right now, its surface would not stop at Mercury. It would not stop at Venus. It would not stop at Earth or Mars or the asteroid belt. That the surface of Betelgeuse would extend past the orbit of Jupiter. Everything from the Sun to Jupiter would be inside the star. The inner solar system would simply cease to exist, swallowed by the distended body of a single dying star. Betelgeuse is roughly 764 times the diameter of our Sun. If you could hollow it out and fill it with suns, you could fit more than 400 million of them inside, and yet, despite its unimaginable volume, as Betelgeuse is only about 15 to 20 times more massive than the Sun. It is vast but tenuous, bloated, swollen, a star that has puffed itself out to hundreds of millions of kilometers because it is running out of fuel and has lost the ability to hold itself together. That is what happens when a massive star begins to die. The core contracts as nuclear fuel runs low, and the outer layers, no longer held in check by the balance of pressure and gravity, expand outward. As the surface stretches and cools, a star that was once compact and blue-white becomes enormous and red. The colour tells you the temperature. Blue stars are hot, white stars are very hot. Yellow stars like our Sun are moderately hot. Red stars are cool, at least by stellar standards. Betelgeuse's surface temperature is roughly 3,000 to 300 degrees Celsius. That sounds hot, and it is, but it is almost half the temperature of our Sun's surface and a fraction of the temperature of the hottest stars. And so when you look at Betelgeuse and see that red glow, you're looking at a star in the final stages of its life. A star that has burned through its core hydrogen, that is now fusing heavier and heavier elements in a desperate attempt to keep generating energy, and that has swollen to grotesque proportions as the battle between gravity and nuclear fire tilts slowly, inevitably, toward gravity. And here is the part that makes Betelgeuse unlike almost any other object in the night sky. Oh, it is close. Not close in the way that the Moon is close, or even in the way that nearby stars like Alpha Centauri are close, but close enough and large enough that it is one of the only stars in the entire sky whose surface we can actually see. Not as a point of light, as a disk. As a resolved, imaged, mappable surface with features and structures and changes that we can track in real time. Betelgeuse is approximately 650 light-years from Earth. That means the light hitting your eyes tonight, if you step outside and look at Orion, left that star around the year 1376. Before Columbus, before the printing press, before the Renaissance as we know it, that photon has been travelling through the void of interstellar space for 6.5 centuries, and tonight it ends its journey on the back of your retina. That is a connection across time that is difficult to fully grasp, but I want you to hold on to it. Because tonight, we are going to understand what is happening to that star right now, what it is doing at this very moment, 650 light-years away, that we will not see for another 6 centuries. Betelgeuse is young. Not young by human standards, but young by stellar standards. It is somewhere between 8 and 8.5 million years old. Our Sun, by comparison, is 4.6 billion years old and is only halfway through its expected lifespan. That Betelgeuse has burned through its entire main sequence in less than 1/500th the time. It lived fast. Massive stars always do. The more massive a star, the faster it burns its fuel, the shorter its life. Betelgeuse was born in a molecular cloud roughly 10 million years ago, spent most of that time as a hot blue supergiant, and has been in its current red supergiant phase for only about 40,000 years. In cosmic terms, it just arrived, and it will not stay long. And somewhere in the next 100,000 years, possibly much sooner, the core of Betelgeuse will run out of fusible material. When that happens, the outward pressure that has been fighting gravity for 10 million years will vanish, and the core will collapse. In less than a second, The inner regions of the star will implode at a quarter of the speed of light, crashing inward until they reach the density of an atomic nucleus. The collapse will trigger a shockwave that rips the rest of the star apart. This is a core collapsed supernova, and Betelgeuse will almost certainly die this way. But I am getting ahead of the story, because before Betelgeuse dies, there is a mystery to solve, a mystery that took over 100 years to crack. And it begins not with the star's death, but with something much more subtle, something that astronomers began to notice in the late 1800s. And something strange about the way Betelgeuse's light changes over time. For thousands of years, every civilization that looked at Betelgeuse saw the same thing, a single, steady red light, a lone giant, the loneliest king in the sky. But as telescopes improved and astronomers began to measure the brightness of stars with precision, they noticed something unexpected. Betelgeuse was not steady at all, it was changing, dimming and brightening in a pattern that seemed to have a hidden rhythm. And that rhythm would take more than a century to decode. The first rhythm was relatively easy to understand. Betelgeuse brightens and dims on a cycle of roughly 400 days. It swells, then contracts, then swells again. A heartbeat. The star is literally pulsating, expanding and shrinking in a regular pattern driven by the physics of its interior. When the star expands, its surface cools slightly and it dims. When it contracts, the surface heats and it brightens. This is normal behavior for a red supergiant. Many of them do it. The 400-day cycle was identified, understood, and filed away. But there was a second rhythm, a much longer one. Roughly every 2,100 days, roughly every 6 years, Betelgeuse went through a separate, slower cycle of brightness variation. This was called the long secondary period, and nobody could explain it. It was not a pulsation. The timescale was wrong, it was not convection. That the churning of hot and cool regions on the star's surface, because convection is chaotic, not periodic. It was not star spots, which come and go unpredictably. It was not magnetic cycles, which do not produce the kind of smooth sinusoidal variation that the long secondary period showed. Paper after paper attempted to explain it. Hypothesis after hypothesis was proposed, tested, and found wanting. For over a century, the long secondary period of Betelgeuse remained one of the most stubborn unsolved problems in stellar astrophysics. And in the background, quietly, a small number of researchers were suggesting something that sounded almost absurd. What if there was something else there? What if Betelgeuse was not alone? What if the 6-year cycle was caused not by something the star was doing to itself, but by something orbiting it, a companion, a second star, hidden inside the atmosphere of the giant? The idea was not new. Binary star systems are common. Most stars in the Milky Way exist in pairs or groups, but the hypothesis for Betelgeuse seemed almost impossible. How could a companion star survive inside the atmosphere of a red supergiant? How could it avoid being detected by every telescope that had ever looked at one of the most observed stars in the sky? And if it was there, why could nobody see it? Those questions lingered for decades. They were discussed in conference rooms, and journal articles and late-night conversations among astronomers who studied Betelgeuse. But without evidence, they remained speculation. Interesting speculation. Compelling speculation. But speculation nonetheless. And then, in late 2019, Betelgeuse did something that made every astronomer on Earth stop what they were doing and look up. It began to disappear. The change started in September 2019. Betelgeuse, normally one of the top 10 brightest stars in the sky, began to dim. At first, nobody was particularly alarmed. Variable stars dim. That is what they do. But by October, the dimming had not stopped. By November, it was deepening. By December, something was clearly wrong. Betelgeuse had dropped in brightness to a level that had not been recorded in over 150 years of continuous observation. And then, it got worse. By January 2020, the dimming was visible to the naked eye. Yet if you walked outside on a clear winter night and looked at Orion, you could see it with your own eyes. The left shoulder of the hunter was fading. Betelgeuse, one of the most familiar stars in the sky, was almost missing from the constellation. The balance of the figure looked wrong. Orion looked lopsided, diminished, incomplete. By February 2020, Betelgeuse had lost more than a third of its brightness. This was unprecedented. The internet erupted with speculation. News outlets around the world ran the same headline with minor variations. Is Betelgeuse about to explode? The question was not unreasonable. Betelgeuse is a star that will go supernova. That is certain. And one of the possible precursors to a core collapse supernova is rapid, dramatic changes in the star's behaviour. Nobody knows exactly what a star looks like in the final weeks or months before it explodes because no one has ever watched a nearby supergiant in the moments before detonation. The sample size for that observation is 0, so when the most famous red supergiant in the sky began dimming in a way that had never been seen before, the possibility of an imminent supernova could not be immediately ruled out. What would a Betelgeuse supernova look like from Earth? The answer is spectacular. At 650 light-years away, the explosion would appear roughly as bright as the full moon. It would be visible in broad daylight. Yet you would be able to walk outside at noon and see a new star burning in the sky, beside the sun. At night, it would cast shadows, a point of light so intense that you could read a book by its glow. The light show would last for weeks at peak brightness, then gradually fade over the course of a year or more. The expanding remnant, a cloud of gas and dust hurled outward at thousands of kilometers per second, would remain visible as a nebula for thousands of years, and at 650 light-years, Earth would be completely safe. No harmful radiation, no gravitational disruption, no danger whatsoever. Just the most extraordinary astronomical event in recorded human history, visible to every person on the planet. So when Betelgeuse began dimming in 2019, the excitement was genuine. Not because anyone wanted the star to die, but because witnessing a supernova that close, in real time, would be a once-in-a-civilization event. The last supernova visible to the naked eye from Earth was in 1604, more than 400 years ago, and it was farther away and fainter than what Betelgeuse would produce. But Andrea Dupree was not thinking about supernovae. She was thinking about data. Dupree is an astronomer at the Harvard-Smithsonian Center for Astrophysics and one of the world's foremost experts on Betelgeuse. She had been observing the star with the Hubble Space Telescope periodically since January 2019, a month before the dimming began, and in those observations, taken in the ultraviolet wavelengths that Hubble excels at, she had seen something that most people had missed. In the fall of 2019, just as the dimming was beginning, Hubble detected a massive blob of superheated plasma erupting from the surface of Betelgeuse. The material was moving outward at roughly 200,000 miles per hour. It was 2 to 4 times more luminous than the star's normal brightness. Yet it was an enormous outburst of hot gas, ejected from the star's surface with tremendous force, and it was heading outward into the surrounding space. Dupree and her team tracked what happened next. The superheated plasma travelled outward for millions of miles, and as it moved away from the searing heat of the star's surface, it cooled. And as it cooled, something remarkable happened. The elements in the gas, silicon and other heavy metals began to condense. They solidified into tiny grains. Grains of dust. A cloud of freshly formed stardust, hanging in space between the star and Earth, blocking the light. Betelgeuse had sneezed. That is the word Dupree used, and it became the metaphor that stuck. The Great Dimming was not a precursor to a supernova. It was a surface mass ejection, a massive cough of hot gas that cooled into a dust cloud and temporarily blocked the southern hemisphere of the star from view. And images from the European Southern Observatory's Very Large Telescope confirmed it. The dimming was not uniform. It affected only one region of the star's disk. The southern part of Betelgeuse had gone dark, obscured by its own expelled material. By April 2020, the dust had dispersed. Betelgeuse returned to its normal brightness. The world moved on. But Andrea Dupree did not move on. She kept the Hubble observations running, month after month, through 2020, 2021, 2022, 2023, and beyond. But because the Great Dimming, dramatic as it was, had not answered her real question. The dust cloud explained why Betelgeuse dimmed so dramatically in 2019, but it did not explain the deeper pattern. The 6-year rhythm, the long secondary period that had been ticking away like a metronome for over a century, long before the Great Dimming, and that continued ticking after the dust had cleared. Something else was going on, something the sneeze had briefly obscured but not resolved, and something that had been hiding in the data for 100 years, waiting to be found. And in 2024, two separate teams of Rasool researchers working independently came to the same conclusion. They analysed more than 100 years of Betelgeuse brightness data. They built models, they tested every alternative hypothesis, and they found that the only explanation that fit the long secondary period, the only model that reproduced the observed 6-year cycle with the correct amplitude and phase, was a companion star, a small dense object orbiting deep inside Betelgeuse's extended atmosphere, its gravitational influence modulating the gas and dust around it, producing the rhythmic brightness changes that had puzzled astronomers since the 19th century. The companion had to be there. The math demanded it. The data required it. There was no other explanation that worked. But theoretical models are not the same as direct evidence. And you can prove with mathematics that something should exist, but until you see it, until you point a telescope at the right patch of sky and detect the photons yourself, it remains a prediction. And predictions in science are not facts. The companion star had to be found. And finding it was going to be extraordinarily difficult. Because Betelgeuse is one of the brightest stars in the sky. Its light drowns everything around it. Trying to see a faint companion star nestled inside the blinding glare of a red supergiant is like trying to see a firefly sitting on the surface of a lighthouse. The firefly is there. It is emitting its own light. But the lighthouse is so overwhelmingly bright that the firefly's signal is utterly lost. Every major telescope had tried. Hubble had looked in ultraviolet and optical wavelengths. Ground-based observatories had used adaptive optics to sharpen their images. And infrared surveys had searched for the thermal signature of a hidden object. Nothing. Every search came up empty. The companion, if it existed, was too faint, too close to Betelgeuse, and too deeply embedded in the giant's glare to be detected. Then Steve Howell had an idea. Howell is a senior research scientist at NASA's Ames Research Center in California. He studies binary star systems and has spent much of his career developing techniques for resolving closely separated objects in astronomical images. And he knew about a camera that might be able to do what no other instrument had managed. The camera is called al-Jawza. It is a speckle imaging instrument mounted on the Gemini North telescope in Hawaii, one of the largest telescopes in the world. Speckle imaging works differently from conventional imaging. Instead of taking one long exposure, which allows atmospheric turbulence to blur the image, speckle imaging takes thousands of extremely short exposures, each one freezing the atmospheric distortion in place. Then, through careful computational processing, the blur is removed and the true image is reconstructed with extraordinary sharpness. Howell knew that the theoretical predictions gave a narrow window of opportunity. The companion star, if it orbited Betelgeuse every 6 years as the models predicted, that would only be at its maximum distance from the giant, its widest separation, for a few months at a time. During those months, it would be at the very edge of Betelgeuse's visible disk, as far from the blinding centre of the giant as it ever gets. That was the window. Miss it, and you would have to wait 3 years for the companion to orbit around to the other side and reach maximum separation again. Howell pointed the Gemini telescope at Betelgeuse during that window. The al-Jawza camera fired. The thousands of short exposures were captured, the data was processed, and there it was, a faint blue-white dot, exactly where the models predicted it would be, sitting at the very edge of Betelgeuse's disk, barely separated from the overwhelming red glare of the giant. Small, dense, rural. In July of 2025, the results were published. For the first time in the history of astronomy, the companion star of Betelgeuse had been directly detected. They measured it. At approximately 1.4 to 1.6 times the mass of our Sun. A main sequence star. Hot. Blue-white, likely spectral type A or late B. A perfectly normal star by any standard, except for the extraordinary fact that it was orbiting inside the atmosphere of a red supergiant 400 million times the Sun's volume. The star needed a name, and Steve Howell chose one that honoured the Arabic roots of Betelgeuse itself. Betelgeuse comes from Yad al-Jawza, the hand of the powerful one. So Howell named the companion Siwarha, an Arabic word meaning her bracelet. The bracelet on the hand, a small bright ornament circling the wrist of a giant. The International Astronomical Union officially recognised the name on September 22, 2025. Siwarha was real. After a century of speculation, after decades of failed searches, after every other explanation had been exhausted, The hidden companion had been found. The loneliest star in Orion was not alone. It had never been alone. That it just took us 100 years to notice. But finding Siwarha was only the beginning, because now that scientists knew where the companion was, they could ask the question that mattered most. Not where is it, but what is it doing? What effect is this small star having on the enormous dying giant it orbits? And is that effect the key to understanding everything we have observed about Betelgeuse for the past century? Months after the discovery, the Hubble Space Telescope answered that question, and the answer was far more dramatic than anyone had imagined. On January 5th, 2026, at the 247th meeting of the American Astronomical Society in Phoenix, Arizona, Andrea Dupree stood before an audience of astronomers and presented what she had found. She had been collecting Hubble data on Betelgeuse continuously for nearly 8 years, spectra, velocity measurements, atmospheric profiles. An unprecedented dataset tracking the behaviour of a single star's atmosphere over the better part of a decade. And when she analysed that data with the knowledge that Siwarha was there, orbiting inside the atmosphere, a pattern emerged that had been invisible before. She found a wake, a trail of dense, compressed gas carved through Betelgeuse's outer atmosphere. Not random, not chaotic, a structured, repeating disturbance that appeared at the same point in the 6-year cycle every time. The wake appeared each time Siwarha crossed in front of Betelgeuse from our perspective, passing between the giant star and Earth. As the companion moved through the tenuous outer layers of the supergiant's atmosphere, it dragged gas along with it, compressing it, heating it, leaving a trail of denser material in its path. Dupree described it with an image that immediately became the defining metaphor for the discovery. "It is a bit like a boat moving through water," she said. The companion star creates a ripple effect in Betelgeuse's atmosphere that we can actually see in the data. A boat through water, a small star through the body of a giant, leaving a visible trail. The wake explained everything. It explained the long secondary period, the 6-year brightness cycle that had baffled astronomers for over a century. As Siwarha orbited, its wake modulated the density of gas and dust around Betelgeuse, alternately blocking and clearing the star's light in a smooth, periodic pattern. The mystery that had resisted 100 years of investigation was solved in a single observation. It was Siwarha. It was always Siwarha. The hidden companion, carving its path through the atmosphere of a dying star, shaping what we saw from 650 light-years away without anyone knowing it was there. But the discovery of the wake raised a new question. A question about physics. About the fundamental mechanics of what happens when a solid object moves through a medium that resists its motion. If Siwarha is ploughing through Betelgeuse's atmosphere, then Betelgeuse's atmosphere is resisting Siwarha's motion. The gas that Siwarha pushes through is not nothing. It is thin, incredibly thin by terrestrial standards, but it is not vacuum. It has mass, it exerts drag. And drag, in orbital mechanics, has consequences. The process is called dynamical friction. But when an object moves through a medium, even a very thin one, the gravitational interaction between the object and the material around it creates a net force that opposes the object's motion. The object slows down. And in orbital mechanics, an object that loses energy does not simply slow to a stop, it falls inward, closer to the centre of gravity, closer to the core. This is one of the most counterintuitive results in physics. When a spacecraft in orbit fires its engines to slow down, and it does not hover in its into place, it drops to a lower orbit. It gets closer to the thing it is orbiting. The same principle applies to Siwarha. Every orbit, every 6-year passage through Betelgeuse's atmosphere, the drag steals a tiny amount of energy from the companion. And with each stolen increment of energy, Siwarha's orbit shrinks. It falls a little closer, a little deeper into the body of the giant. The timescale is long, thousands of years, perhaps tens of thousands. But the direction is certain. Siwarha is spiralling inward. Not dramatically, not visibly, not on any human timescale, but with the quiet, patient inevitability of gravity and friction, two forces that never rest and never reverse. Currently, Siwarha orbits at a distance of approximately 4 astronomical units from Betelgeuse's core. 4 astronomical units. In our solar system, that is roughly the distance from the Sun to the asteroid belt, a little less than the distance to Jupiter. But Betelgeuse is so enormously swollen that 4 astronomical units is still inside the star's atmosphere. Siwarha is orbiting within the body of Betelgeuse, not outside it. The companion is submerged, embedded, buried in the outer layers of a star that extends for hundreds of millions of kilometers in every direction. And it is getting closer. The spiral will continue, orbit by orbit, century by century. The drag will accumulate, the orbit will thus shrink, and at some point, on some timescale that astrophysicists are still working to constrain, one of 2 things will happen. Either Siwarha will spiral close enough to the core that tidal forces tear it apart and it merges with Betelgeuse in a violent, luminous event that could briefly make the star flare brighter than anything it has done in millions of years. Or Betelgeuse will run out of fuel first, the core will collapse, the supernova will fire, and Siwarha, caught in the blast, will either be destroyed, swallowed by the expanding shockwave, or flung outward at tremendous velocity, a hypervelocity star ejected from the ruins of its dead companion, racing out of the Milky Way and into the intergalactic void. Which happens first? Does Siwarha reach the core, or does the core reach Siwarha? That question does not have an answer yet. It depends on variables that are not yet precisely measured. The density profile of Betelgeuse's atmosphere, the exact mass and orbit of Siwarha, the rate of Betelgeuse's internal evolution, which determines how quickly it progresses toward core collapse. These are active areas of research. The data from Hubble, from Gemini, from the upcoming observations in 2027 when Siwarha re-emerges to maximum separation, will all contribute to narrowing the uncertainty. But what we can say, with confidence, is this. Betelgeuse and Siwarha are not going to grow old together. They were born together, from the same molecular cloud, roughly 10 million years ago. One became a monster, swelling to consume everything within hundreds of millions of kilometers of its core. The other stayed small, compact, unremarkable. And now the monster is slowly, inevitably pulling its smaller sibling deeper into itself. 2 stars born as companions, ending as one, or ending in an explosion that scatters their combined material across light years of space. There is something almost unbearably poetic about that. 2 stars, born together in the same cloud of gas and dust, spending 10 million years in each other's company, and now approaching an ending that neither can escape. It is not a human story, not really. Stars do not feel loneliness or companionship or grief, but the structure of it, the arc from shared origin to inevitable parting, maps onto something deeply human. And perhaps that is why Betelgeuse has always fascinated us. Not just because it is big or bright or close, but because its story, in some fundamental way, echoes our own. If you are still with me, if this journey has kept you company tonight, I want you to know that your being here matters. A like on this video, a subscription to Science for Sleep, these small gestures are what allow us to keep telling these stories. The subscribe button is just below, and now let us continue, because Betelgeuse's story is not finished, not by a long way. What happens when Betelgeuse finally dies? We know that it will happen. That's not in question. Betelgeuse is a red supergiant that has exhausted its core hydrogen and is fusing heavier elements in a series of increasingly desperate nuclear reactions. Hydrogen fused into helium, helium into carbon and oxygen, carbon into neon and magnesium. Each stage is shorter than the last. Each stage produces less energy. Each stage brings the star closer to the moment when the core is made of iron and iron cannot be fused for energy. When the core becomes iron, yet the nuclear furnace goes out. And when the furnace goes out, gravity wins. The collapse takes less than a second. The core, roughly 1.5 times the mass of the Sun, implodes at a quarter of the speed of light. It compresses until it reaches the density of an atomic nucleus, roughly 100 trillion grams per cubic centimeter. The infalling material rebounds off this incompressible core, generating a shockwave that propagates outward through the entire star. That shockwave tears Betelgeuse apart. The energy released in a core collapse supernova is almost beyond quantification. For a brief period, the dying star outshines its entire host galaxy. Billions of stars, and one dying star burns brighter than all of them combined. The outer layers of the star are hurled outward at speeds of 10,000 to 30,000 kilometers per second, carrying with them every heavy element the star manufactured during its lifetime. Carbon, oxygen, silicon, iron, nickel, gold, platinum. and every atom heavier than hydrogen and helium that exists in the universe was forged in a star and dispersed by a supernova, including the atoms in your body. The calcium in your bones was made in a star like Betelgeuse. The iron in your blood was synthesized in a stellar core and scattered by an explosion just like the one that will eventually destroy Betelgeuse. You are, in the most literal and non-metaphorical sense, made of dead stars. When Betelgeuse explodes, what will it look like from here? From our quiet little planet 650 light-years away? The answer is unlike anything any living human has ever seen. At peak brightness, the supernova will be roughly as bright as the full moon. It will be visible during the day. You will be able to walk outside at noon, look up and see a point of light burning in the sky beside the sun, not a streak like a meteor, not a faint dot like Venus, a blazing point of light clearly visible in full daylight, hanging in the region of Orion. At night it will be extraordinary. The supernova will cast visible shadows on the ground. You will be able to stand outside and read by its light. Orion will look transformed. The familiar pattern of the hunter dominated by a single brilliant point where the red shoulder used to be. The constellation will never look quite the same again. Peak brightness will last for several weeks. Then the supernova will gradually fade over the course of months. That it will remain visible to the naked eye for over a year. As it fades, the expanding remnant, the cloud of gas and dust hurled outward by the explosion, will become visible through telescopes as a growing nebula, eventually stretching across a significant patch of sky. That nebula will be visible for thousands of years. Humanity's descendants, whoever and wherever they are, will look up and see the ghost of Betelgeuse still glowing in Orion. And here is the part that people always ask about. And is it dangerous? At 650 light-years, the answer is no, not even slightly. The harmful radiation from a supernova, the gamma rays and high-energy particles that can strip atmospheres and sterilize surfaces, drops off with the square of the distance. At 650 light-years, the radiation reaching Earth would be indistinguishable from background. Our atmosphere and magnetic field would absorb what little arrived. There would be no effect on Earth's biosphere, no mass extinction, no radiation damage. It's just the most spectacular light show in recorded human history. The timing remains unknown. Somewhere in the next 100,000 years, it could be 100,000 years from now, it could be 10,000 years. In principle, it could be next week. We do not know how to predict with any precision when a star will go supernova. The final stages of core evolution happen quickly by stellar standards but still span timescales of years to millennia. There are no warning signs that we know how to read with certainty. And the Siwarha discovery has added a new layer of uncertainty. If the companion is affecting Betelgeuse's mass loss rate, if the wake is stripping material from the giant's atmosphere faster or slower than models assumed, then the timeline to supernova could be different from what was previously calculated. Siwarha's presence changes the equation. How much it changes the equation is something scientists are still working out. What we do know is that when the end comes, that whether in 1,000 years or 100,000, Siwarha will still be there, spiraling closer, dragging its wake through the atmosphere of a star on the edge of oblivion. And when the core collapses, Siwarha will face its own moment of truth. If it is close enough to the core, the supernova blast wave will engulf it, potentially stripping away its outer layers or destroying it entirely. If it is far enough away, the sudden disappearance of Betelgeuse's gravitational pull, at which vanishes in the instant the mass is ejected, could unbind Siwarha from the system, sending it flying outward at enormous velocity. A hypervelocity star. A refugee from a catastrophe. A small blue-white survivor, carrying the angular momentum of a 10-million-year orbit, flung out of Orion and into the galaxy at large. Or perhaps Siwarha survives the blast but remains bound to whatever remnant Betelgeuse leaves behind, a neutron star roughly 20 kilometers across, is spinning hundreds of times per second, possessing a magnetic field trillions of times stronger than Earth's. If Siwarha ends up in a tight orbit around this neutron star, the system would become an X-ray binary, a source of high-energy radiation as the neutron star's gravity pulls material from Siwarha's surface. Two stars born together, transformed by 10 million years of evolution into something utterly alien. We do not know which of these outcomes will occur. That is not a failure of science. It is an honest acknowledgement of the limits of prediction for a system this complex, this dynamic, and this unprecedented in our observational experience. Betelgeuse and Siwarha are teaching us things about stellar evolution that no textbook has ever contained, because no one has ever watched a system like this in real time before, and that is why Betelgeuse matters beyond Betelgeuse. It is not just one star, it is a laboratory, the closest, brightest, and most accessible example of a red supergiant in the final stages of its life. Everything we learn about Betelgeuse, about its mass loss, about its atmospheric dynamics, about the influence of a companion on a dying giant, about the physics of pre-supernova evolution, informs our understanding of every massive star in the galaxy. There are thousands of red supergiants in the Milky Way. Most are too far away and too faint to study in detail. Betelgeuse is the one we can see up close. Earth is the one we can resolve, image, and monitor. The Rosetta Stone of stellar death. And now we know it has a companion that has been shaping its behaviour, modulating its brightness, carving trails through its atmosphere, and slowly spiralling toward a rendezvous that will end in merger or explosion. Every observation we make of Betelgeuse from now on must account for Siwarha. Every model, every prediction, every hypothesis about what this star will do next. Though the companion changes everything. In November 2027, Siwarha will complete the far side of its current orbit and re-emerge to maximum separation from Betelgeuse. For the first time since its discovery in 2025, it will be in the optimal position for detailed study. Every major observatory on Earth and in space will be watching. The James Webb Space Telescope, with its infrared eyes, could potentially characterize Siwarha's temperature and composition directly. The ground-based extremely large telescopes, the next generation of instruments currently under construction in Chile and Hawaii, may have the resolution to image the wake itself, to see the trail of compressed gas being carved through Betelgeuse's atmosphere in real time. We are at the beginning of a new era in our understanding of this star. Everything that came before, the century of brightness measurements, the decades of spectroscopic monitoring, the drama of the Great Dimming was prologue. The real story starts now, with two stars, one dying, one spiralling inward, both writing their final chapter in a language we are only just learning to read. But the story of Betelgeuse does not begin with modern astronomers and their space telescopes. It does not begin with Hubble or Gemini or the Very Large Telescope. It begins much further back, in an era when the tools of astronomy were nothing more than patience, naked eyes, and an unobstructed view of the night. The earliest recorded observations of Betelgeuse's colour come from the ancient world. The Greek astronomer Ptolemy, writing in the 2nd century, included Betelgeuse in his star catalogue and described it as reddish. That description has been consistent across nearly 2,000 years of observation. Every astronomer who has looked at Betelgeuse since Ptolemy has agreed, it is red, unambiguously, unmistakably red. But here is a detail that most people overlook. And a star's colour is not permanent. Colour tells you temperature. Temperature tells you what stage of life the star is in. A star that is red today was not always red. Betelgeuse, in its youth, when it was still burning hydrogen in its core on the main sequence, would have been blue. A brilliant, blazing, blue-white supergiant, thousands of times more luminous than it is now, but compressed into a much smaller volume. If you had stood on Earth 10 million years ago, before humans existed, before the genus Homo had even begun to emerge, and looked up at the constellation we now call Orion, you would not have seen a red star on the hunter's shoulder. You would have seen a blue one, brighter, hotter, more compact, and very much alive. The transition from blue to red happened relatively recently in Betelgeuse's life. Roughly 40,000 years ago, the star exhausted the hydrogen in its core and began to expand. Its surface cooled as the outer layers stretched outward. The blue faded to white, then to yellow, then to orange, then to the deep red we see today. Aboriginal Australians who have been observing the sky continuously for at least 65,000 years may have witnessed this transition. Their astronomical traditions, passed down through oral history across thousands of generations, contain references to stars that changed colour. Some researchers have speculated that stories about Betelgeuse in Aboriginal tradition may encode a memory of the star's transition from blue to red, a memory that would predate every written record in existence. If that is true, and the evidence is suggestive but not conclusive, then the Aboriginal Australian astronomical tradition contains a direct observational record of a star evolving from the main sequence to the red supergiant phase. and a record encoded not in data files or journal articles, but in stories told around fires under the southern sky, passed from elders to children for 2,000 generations, the longest continuously maintained scientific observation in human history, and it was never written down. That is worth sitting with for a moment. The idea that the most ancient observers of Betelgeuse may have seen it as a fundamentally different star than the one we see today. And that the red glow we associate with Betelgeuse is not eternal but recent, a phase, a stage, costume the star put on only 40,000 years ago as it began its slow march toward death. Before that, for millions of years, it burned blue, and after it explodes in whatever distant century or millennium that occurs, the red will be gone too, replaced by the blinding white of a supernova fireball, then by the fading glow of an expanding nebula, then by nothing at all. Just a neutron star or a black hole, invisible to the naked eye, occupying the space where a star once burned. Orion's shoulder empty. The hunter, incomplete. Now let us go inside the star one more time, not to the outer atmosphere where Siwarha orbits, but deeper, all the way down to the core, because what is happening at the centre of Betelgeuse right now, at this very moment, 650 light-years away, determines everything about how the story ends. The core of Betelgeuse is a nested structure, but like the layers of an onion, at the very centre, the densest, hottest region, nuclear fusion is converting carbon into neon and magnesium, and possibly neon into oxygen and magnesium. Each layer outward is burning a lighter element. The carbon-burning core is surrounded by a shell of helium fusion. The helium shell is surrounded by a shell of hydrogen fusion. Each shell is thinner and cooler than the one below it. The whole structure is held in a precarious balance, gravity pulling inward, the nuclear energy pushing outward, with each layer providing just enough pressure to prevent the layer above it from collapsing. This balance is not so stable. It is more like a juggler keeping 7 balls in the air simultaneously while standing on a ball themselves. Each nuclear burning stage is shorter than the last, because each successive fuel produces less energy per reaction, and the core needs more reactions per second to maintain the outward pressure. The hydrogen burning on the main sequence lasted roughly 8 million years. Helium burning lasted perhaps 1 million years. Carbon burning lasts a few thousand years. Neon burning, when it begins, will last roughly a year. Oxygen burning will last months. And the final stage, silicon burning, the last fuel that produces energy through fusion, lasts approximately 1 day. 1 day. After 10 million years of nuclear burning, the final stem lasts 24 hours. At the end of silicon burning, yet the core is made of iron. Iron is the end of the line. Iron is the most tightly bound nucleus in nature. You cannot extract energy by fusing iron into heavier elements. The nuclear furnace, which has kept Betelgeuse alive for 10 million years, producing energy from hydrogen, then helium, then carbon, then neon, then oxygen, then silicon, finally reaches a fuel it cannot burn. And in that moment, the furnace goes out. What happens next takes less than a second. Without nuclear energy to support it, the iron core collapses under its own gravity. The collapse is catastrophic. The inner core, roughly 1.5 solar masses of iron and nickel, implodes at velocities approaching 1/4 of the speed of light. In roughly 1/10 of a second, the core goes from being roughly the size of Earth to being roughly the size of a city. The density increases from millions of grams per cubic centimetre to hundreds of billions of grams per cubic centimetre. The temperature soars to over 100 billion degrees. Protons and electrons are forced together to form neutrons. The core becomes a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain. The outer core, still falling inward, slams into the newly formed neutron star and rebounds. This rebound sends a shockwave outward through the star, but the shockwave alone is not powerful enough to blow the star apart. It stalls within milliseconds, and its energy absorbed by the still in falling outer layers. For a brief, terrifying moment, the star is in limbo. The core has collapsed, but the explosion has not succeeded. The shockwave has stalled. The star is dying, but not yet dead. What reignites the explosion are neutrinos. The newly formed neutron star radiates an incomprehensible flood of neutrinos, ghostly particles that barely interact with matter. In the incredibly dense environment of the collapsing star, even neutrinos, which can normally pass through light years of solid lead without stopping, deposit a fraction of their energy into the stalled shockwave. That energy boost is enough. The shockwave revives, it accelerates outward through the star, heating and compressing the material in its path, triggering new nuclear reactions, synthesizing elements heavier than iron through a process called rapid neutron capture. Gold, platinum, uranium, the heaviest elements in the periodic table, they're elements that cannot be made in any now normal stellar process, are forged in the few seconds of the supernova explosion itself. The shockwave reaches the surface of the star within hours. When it breaks through, the outer layers of Betelgeuse are hurled into space at speeds of 10,000 to 30,000 kilometers per second. The released energy, roughly 10 to the power of 46 joules, is more energy than the Sun will produce in its entire 10 billion year lifetime, released in a matter of seconds. For a few weeks, the dying star outshines everything in its galaxy. Billions of stars, and one death outshines them all. The expelled material, carrying the full catalogue of elements that Betelgeuse manufactured over 10 million years, expands outward into the interstellar medium. It mixes with existing gas and dust. It enriches the surrounding space with carbon, oxygen, nitrogen, silicon, iron, and all the heavier elements produced in the explosion. Over millions of years, this enriched material will gather into new molecular clouds. Those clouds will collapse into new stars. Those stars will form new planets, and those planets will be made in part of atoms that were once inside Betelgeuse. This is not a poetic abstraction. This is a direct, physical, measurable chain of causation. The elements in your body were made in stars at specific times in specific nuclear reactions. The iron atoms in your hemoglobin were synthesized in the core of a massive star and scattered by a supernova explosion roughly 5 billion years ago, before the Sun existed, before the Earth formed. Different iron atoms in your body may have come from different stars, different supernovae, different locations in the galaxy. You are quite literally a collection of atoms assembled from the debris of multiple stellar explosions gathered together by gravity into a planet, just organized by chemistry into molecules, animated by biology into a living being that is now lying in the dark, listening to a story about the star that will produce the next generation of those atoms. The calcium that strengthens your bones right now was once inside a star, not metaphorically, literally. The phosphorus in your DNA was forged in stellar nucleosynthesis. The oxygen you are breathing was produced by a star-like Betelgeuse ejected in a supernova, that incorporated into a molecular cloud, swept up by the forming solar system, and trapped in Earth's atmosphere 4.5 billion years ago. Every breath you take connects you to the death of a star, and when Betelgeuse finally dies, its atoms will begin that journey again, scattered into space and mixed into nebulae, incorporated into future worlds. The cycle of stellar birth and death is the cycle that produces everything, every planet, every ocean, every molecule of water, and every strand of DNA. Every living thing that has ever existed on any world in the galaxy owes its existence to the death of stars. Betelgeuse is a chapter in that story, one chapter among billions, but it is the chapter we can read most clearly because it is happening right now, 650 light years away. Close enough to see, close enough to study, close enough to understand. And now, with Siwarha discovered, with the wake detected, with the mystery of the long secondary period solved, we can read that chapter with more clarity than ever before. The story of Betelgeuse is a story about death, but it is not a sad story. It is a story about transformation, about the way the universe recycles itself, endlessly, using the deaths of old stars to fuel the births of new ones, about the way that nothing is truly lost, only rearranged. The atoms that are inside Betelgeuse tonight will be inside something else in 1 billion years. Here's something new. There's something that could not have existed without the death that created it. That is the deepest truth that stellar astrophysics has ever revealed. Death is not an ending. It is a dispersal, a scattering, a return of borrowed material to the cosmic commons, where it will be borrowed again by the next generation of stars and planets and perhaps living things. Betelgeuse is going to die, that is certain, and when it does, the universe will be richer for it. There is something else about Betelgeuse that rarely makes it into their headlines, but that deserves a place in this story. Something about what surrounds the star, beyond Siwarha, beyond the atmosphere, in the space between Betelgeuse and the rest of the galaxy. Betelgeuse is moving. Not just sitting in Orion, static and unchanging, but travelling through the interstellar medium at roughly 30 kilometers per second relative to the surrounding gas. That is fast enough to create a bow shock and a compressed wave of gas ahead of the star, like the wave that builds in front of a boat moving through water. Infrared telescopes have imaged this bow shock. It extends roughly 3 light-years ahead of Betelgeuse, a vast arc of heated gas and dust being pushed aside by the star's motion through the galaxy. The bow shock is enormous, spanning a region of space larger than the distance between the Sun and its nearest stellar neighbour. And behind the bow shock, trailing the star like a comet's tail, is a long, narrow stream of expelled material. Gas and dust that Betelgeuse has been shedding for millennia, left behind as the star moves forward through space. This trail stretches for multiple light-years behind the star and contains material that Betelgeuse ejected thousands of years ago. Material that is still glowing faintly in the infrared, still warm enough to be detected, still carrying the chemical signature of the star that produced it. And when Betelgeuse goes supernova, this entire structure, the bow shock, the trailing debris, the expelled shells of gas from earlier mass loss events, will be swept up by the supernova blast wave and incorporated into the expanding remnant. The remnant will not be spherical. It will be shaped by the environment the explosion occurs in. The bow shock in front and the trail behind will create asymmetries, producing a supernova remnant that is elongated, irregular, and uniquely shaped by the conditions of the space Betelgeuse has been travelling through for millions of years. Astronomers have already modelled what this remnant might look like. It will not resemble the neat symmetric shell of a textbook supernova remnant. It will be messy, lopsided, beautiful in its asymmetry. A cosmic sculpture shaped by the interaction of an unimaginably powerful explosion with the delicate structure of the interstellar medium. And for thousands of years after the explosion, that remnant will be visible from Earth. A glowing cloud in the direction of Orion, slowly expanding, slowly fading, slowly dispersing into the galaxy. Generations of humans who never saw Betelgeuse as a star will know it only as a nebula, a ghost, a remnant of something that used to be. Let us talk about distance one more time, because distance in astronomy is not just a measurement, it is a relationship with time. And the relationship between Earth and Betelgeuse is one of the strangest time relationships in the observable sky. Betelgeuse is approximately 650 light-years away. That means the light we see tonight left the star around the year 1376. The 100 Years' War was being fought in France. The Black Death was still a living memory in Europe. The Ming dynasty was in its early decades in China. The Aztec Empire had not yet been founded. Chaucer had not yet written the Canterbury Tales. And everything you associate with the modern world, every nation, every technology, every idea that shapes your daily life did not exist when the photon that is hitting your retina right now departed from the surface of Betelgeuse. And here is the disorienting part. What we see is not what is happening. What we see is what happened 650 years ago. Betelgeuse right now, at this very moment in March 2026, is doing something. Siwarha is orbiting. The wake is being carved, gas is being expelled. The core is burning through its fuel, but we will not see any of that for another 650 years. The light carrying the information about what Betelgeuse is doing tonight will not reach Earth until approximately the year 2676. It is entirely possible that Betelgeuse has already gone supernova. The explosion could have happened yesterday, or 100 years ago, or 500 years ago, and we would not know yet. The light from the explosion is still travelling toward us, so we're crossing the void at 300,000 kilometers per second and it has not arrived. We are watching a movie that was filmed 650 years ago, and the ending has not reached us yet. This is one of the most disorienting truths in astronomy. We never see the universe as it is. We see the universe as it was. Every observation is a look backward in time. The sun we see is the sun as it was 8 minutes ago. The moon is the moon as it was 1.3 seconds ago. Jupiter, when it is at its closest to Earth, and is Jupiter as it was roughly 33 minutes ago. And Betelgeuse is Betelgeuse as it was 650 years ago. We live in a universe of delayed information. Every direction we look, we are looking into the past. The deeper we look, the further back in time we see. The most distant objects visible to the James Webb Space Telescope are galaxies, as they existed over 13 billion years ago, when the universe was less than 400 million years old. We see them as they were then. What they look like now, 13 billion years later, is information that has not yet had time to reach us. Betelgeuse exists in this web of delayed information like every other object in the sky, and the poignancy of that delay is this. When the supernova finally happens, when the core collapses and the shockwave tears through the star and Siwarha faces its moment of truth, the event will have already occurred by the time the light reaches us. We will not see it in real time. We will see it 650 years after the fact. The explosion will be ancient history by the time we witness it. And yet, we watch. We point our telescopes at Betelgeuse night after night, year after year, knowing that we are watching the past, knowing that the present is hidden from us behind a curtain of light travel delay. We watch because the past is all we have. In astronomy, there is no present. There is only the past, arriving at the speed of light, and the future, hidden behind the horizon of the photons that have not yet reached us. Let us think for a moment about what an observer near Betelgeuse would see if they looked toward us. An observer orbiting at a safe distance from the red supergiant, with a sufficiently powerful telescope who pointed their instrument toward a faint yellow star 650 light-years away, in the direction of the constellation that, from their perspective, does not look anything like it does from ours. They would see our Sun, a modest G-type main-sequence star, unremarkable. One of hundreds of billions of similar stars in the galaxy. If their telescope were powerful enough, which is a significant if, they might detect the tiny wobble in the Sun's light caused by the gravitational tug of Jupiter. They might infer the existence of planets, but they would not see Earth as it is today. They would see Earth as it was 650 years ago. They would see the year 1376. If they could somehow image the surface of our planet, they would see medieval Europe, pre-Columbian Americas, and Song Dynasty China in its late phases. They would see a world without electricity, without telescopes, without any awareness that Betelgeuse was anything other than a red dot in the sky. They would have no way of knowing that 650 years in their future, the inhabitants of that unremarkable planet would discover a companion star hidden inside their red supergiant neighbour. They would have no way of knowing that those inhabitants would name the companion Siwarha, and after the Arabic word for bracelet. They would have no way of knowing that the act of discovery, the simple human act of pointing a telescope and paying attention, would be happening at all. 2 points in space, 2 moments in time, connected by light, separated by centuries, each seeing the other's past, neither seeing the other's present. This is the fundamental condition of observation in a relativistic universe. We are all watching each other's history unfold. The present is always local. The universe is always delayed. And Betelgeuse does not care. It burns, it pulsates, it sheds mass into the void. Siwarha orbits, carves its wake, spirals closer. The core fuses heavier and heavier elements in an accelerating sequence that will end in iron and collapse. None of this is affected by whether anyone is watching. The universe operates regardless of observers. So the physics is the same whether or not a species 650 light-years away has built telescopes sophisticated enough to detect a wake in a stellar atmosphere. But we watch anyway, and in watching we transform what would otherwise be a purely physical process, atoms interacting according to the laws of nature, into a story, a narrative with characters and tension and mystery and resolution, a story about a dying giant and its hidden companion. And a story that will outlast both stars and the species that told it. That is perhaps the most remarkable thing about Betelgeuse, not its skins, or its colour, or its companion, or the wake, or the impending supernova. The most remarkable thing is that it has been observed, that a species arose on a nearby planet, developed the capacity for curiosity, invented instruments to extend its senses, pointed those instruments at a red star in the winter sky, and slowly, painstakingly over centuries, had decoded its secrets. That is the part of the story that no physical model can predict, the emergence of observers, the act of paying attention, decision to wonder. Betelgeuse would exist without us, but it would not be understood, And understanding, in a universe that is otherwise mindless, is not an afternoon nothing. It might be the most extraordinary thing that has ever occurred in this corner of the galaxy. There is a question that deserves more time than it usually gets, and a question that sits underneath everything we have discussed so far, quietly, like the companion star itself sat quietly inside Betelgeuse for 100 years before anyone noticed. How do you hide a star inside another star? It sounds like a riddle, and in a way it is. But the answer reveals something profound about the nature of red supergiants, about the difference between what we see and what is actually there, and about the extraordinary conditions that exist inside the atmosphere of a dying star. When we talk about Betelgeuse's atmosphere, we are not talking about a thin shell of gas like Earth's atmosphere. Earth's atmosphere is a delicate layer, roughly 100 kilometers thick if you are generous with the definition, sitting atop a solid rocky surface. If you scaled Earth down to the size of a basketball, the atmosphere would be thinner than a coat of paint. It is fragile, tenuous, and a breath of gas clinging to a ball of rock. Betelgeuse's atmosphere is nothing like that. There is no solid surface beneath it. There is no clear boundary between the star and the space around it. Betelgeuse is a ball of gas all the way through, from the dense nuclear furnace at the core to the wispy outer layers that trail off into the interstellar medium. And those outer layers are enormous. The visible surface of Betelgeuse, the photosphere, the layer that emits the red light we see, that sits at roughly 764 solar radii from the centre. But the atmosphere extends far beyond that. Gas and dust expelled by the star over millennia form a diffuse envelope that reaches out for hundreds of astronomical units in every direction. If Betelgeuse were placed at the centre of our solar system, its atmosphere would extend well past the orbit of Pluto, and somewhere in that vast, diffuse, tenuous envelope of gas, Siwarha is orbiting. At 4 astronomical units from the core, and it is well inside the extended atmosphere but far outside the dense photosphere. Think of it this way. If Betelgeuse's photosphere is the visible surface of the ocean, then Siwarha is orbiting in the fog above the water. Not in the deep water, not on the surface, in the mist. The gas at Siwarha's orbital distance is extraordinarily thin. By earthly standards, it would qualify as a very good vacuum. But it is not nothing. It has mass, it has density. And when a star-sized object plows through it at orbital velocities, it creates effects that are measurable across 650 light-years of space. And this is what makes the Betelgeuse-Siwarha system so scientifically extraordinary. It is not just a binary star system. There are millions of binary stars in the galaxy. It is a binary system where one component is embedded inside the other, where the smaller star is literally swimming through the atmosphere of the larger one. Look, where every orbit is an interaction, a disturbance, a reshaping of the environment. There is no other system like it that we can observe this closely. Betelgeuse-Siwarha is unique, and that uniqueness is why every major telescope in the world is now pointed at it. Let us go deeper into what that atmosphere actually looks like. Not from the outside as we see it through telescopes, but from the inside, from Siwarha's perspective. Imagine you're riding along with Siwarha. Here you are 4 astronomical units from the core of Betelgeuse, roughly 600 million kilometers from the center of the star. The core itself is far below you, impossibly dense and impossibly hot, fusing carbon and oxygen in nuclear reactions that release floods of energy. But you cannot see the core. Between you and the core are hundreds of millions of kilometers of increasingly dense stellar material. The light from the core is absorbed and re-emitted billions of times as it works its way outward through the star's interior, taking thousands of years to make a journey that light in a vacuum would complete in minutes. Around you, the gas is thin but not invisible. It glows faintly. The temperature at this distance from the core is still thousands of degrees. Not hot enough to sustain nuclear fusion, not hot enough to be truly dangerous to a star like Siwarha. Oh, but hot enough that the gas radiates in the infrared. You are surrounded by a faintly glowing fog of hydrogen, helium, and trace amounts of heavier elements. The fog is not uniform, it has structure. Convection cells from deeper in the star send plumes of warmer gas rising outward, creating eddies and currents in the atmosphere. Cooler gas sinks, the whole system churns slowly, like a pot of water on a very low flame, and through this churning, glowing fog, Siwarha moves at orbital velocity, roughly 30 to 50 kilometers per second depending on its exact position in the orbit. that is fast by human standards but relatively gentle by astronomical ones. As it moves, the gas in front of it compresses, the gas behind it expands. A shock front forms ahead of the companion, and a trailing wake of disturbed, denser gas stretches out behind it. This wake is what Hubble detected. This wake is what solved the century-old mystery of the long secondary period. The wake is not permanent, and it is constantly being created and constantly dissipating. As Siwarha moves forward, the compressed gas behind it gradually re-equilibrates with its surroundings, smoothing out over weeks and months. But Siwarha keeps moving, keeps creating new wake, keeps disturbing the atmosphere in a continuous ribbon of compressed gas that traces its orbital path like the contrail of an aircraft across a clear sky. And except this contrail is millions of kilometers long and is being carved through the body of a star, there is another effect of Siwarha's passage through their atmosphere that scientists are only beginning to model. The companion is not just pushing gas aside, it is gravitationally focusing it. As Siwarha passes through a region of atmosphere, its gravity attracts nearby gas toward it. Some of that gas falls onto Siwarha, adding to its mass in a process called Bondi-Hoyle accretion, and the rest of the gas is pulled into the wake region, increasing its density beyond what simple compression would produce. This gravitational focusing makes the wake denser and more persistent than a purely hydrodynamic model would predict. It is one of the reasons the wake is detectable from 650 light-years away, despite being carved through gas that is, by terrestrial standards, almost empty. The accretion onto Siwarha itself raises another question. Is Siwarha growing? And is it gaining mass as it orbits through Betelgeuse's atmosphere? The answer is almost certainly yes, although the rate is very slow. The amount of mass accreted in each orbit is a tiny fraction of Siwarha's total mass. But over thousands of orbits, over tens of thousands of years, the accumulated mass could begin to matter. It could change Siwarha's spectral characteristics, adding a shell of hydrogen-rich material to a star that was born with a different surface composition. It could, in principle, alter the orbital dynamics by changing the mass ratio between the two stars. These are long-term effects, playing out on timescales far beyond any human observation campaign, but they are real physical consequences of the extraordinary situation these two stars find themselves in. And there is one more consequence of Siwarha's passage through the atmosphere that connects directly to the Great Dimming of 2019. The wake that Siwarha creates is a trail of denser gas, and denser gas is better at condensing into dust when it cools. Dust blocks light. It is entirely plausible, and some researchers have begun to argue that the dust cloud that caused the Great Dimming was not a random event, but was influenced by the density enhancements created by Siwarha's wake. The companion may have created the conditions for the sneeze. The wake may have provided the extra dense pocket of gas that cooled and condensed into the dust cloud that blocked the southern hemisphere of the star. If this is true, and it has not yet been proven, then the most dramatic event in Betelgeuse's recent history, the event that made headlines around the world, was ultimately caused by a star that nobody knew existed at the time. Siwarha, shaping events from the shadows, invisible but consequential. The hidden hand behind the most watched star in the sky. Let us step back now, farther back than Betelgeuse, farther back than Orion, and think about what this discovery means for the rest of the universe. Betelgeuse is not the only red supergiant in the sky. It is not even the only one in our region of the galaxy. There are dozens of red supergiants visible from Earth, and thousands more scattered throughout the Milky Way. Antares, the red heart of Scorpius, is another famous example. Perpetuity Canis Majoris, one of the largest known stars, is another. Mu Cephei, the garnet star, glows deep red in the northern sky. Each of these stars shares Betelgeuse's fundamental nature. They are massive Sietas in the final stages of their lives, swollen beyond comprehension, shedding mass into space, ticking down towards supernova. And here is the thing. Many of these red supergiants show the same kind of long secondary periods that Betelgeuse shows, the same mysterious slow, the periodic brightness variations that could not be explained by pulsation or convection or any other single-star mechanism. For decades, these variations were catalogued and shrugged at. They were filed under Unexplained. They were assumed to be some poorly understood aspect of red supergiant physics that would eventually be worked out. But now, with the Siwarha discovery, a new possibility has opened up. What if those other red supergiants also have hidden companions? What if the long secondary period is not a peculiarity of Betelgeuse, but a signature of embedded companion stars in red supergiants throughout the galaxy? What if this is common? The statistics support this idea. Most massive stars are born in binary or multiple systems. The fraction of massive stars that have at least one companion is estimated to be between 70 and 90%. When one of those stars evolves into a red supergiant and its atmosphere expands to engulf the orbit of its companion, as the companion does not disappear, it keeps orbiting, it becomes embedded, it begins to carve a wake, and from hundreds or thousands of light years away, all we see is a periodic brightness variation that we cannot explain. If this model is correct, and the evidence is growing that it might be, then Betelgeuse is not a special case. It is the first case, the prototype, the one we happen to be close enough and attentive enough to crack open and examine. And every red supergiant with an unexplained long secondary period is now a candidate for a hidden companion search. This is how science works at its best. You study one object in extraordinary detail, you discover something unexpected, and then you realize that the unexpected thing might be everywhere, hiding in plain sight, in every similar object you have ever observed. The particular illuminates the universal. Betelgeuse teaches us about Betelgeuse, but it also teaches us about every massive star in the galaxy that will one day die in a supernova explosion. And there is one more layer to this, one more connection that stretches from Betelgeuse to the deepest questions in astrophysics. When massive stars die in supernovae, they do not just vanish, they leave remnants. Neutron stars, black holes. The nature of the remnant depends on the mass of the core at the moment of collapse. If the core is below roughly 3 solar masses, then it forms a neutron star. Above that threshold, gravity overcomes all other forces and the remnant collapses into a black hole. The mass of the core at the moment of collapse depends on how much mass the star has lost during its lifetime. And how much mass the star loses depends on its wind, its eruptions, its surface mass ejections, and, we now know, the influence of any companion stars embedded in its atmosphere. Siwarha is not just shaping Betelgeuse's brightness. It is shaping how much mass Betelgeuse retains when it finally explodes. It is, in a very real sense, helping to determine whether Betelgeuse leaves behind a neutron star or a black hole. That is an extraordinary statement. A small companion star, 1.5 times the mass of our Sun, orbiting inside the atmosphere of a giant, could be the factor that determines whether the end product of this system is a spinning ball of neutrons 20 kilometers across or a rupture in the fabric of space-time from which nothing, not even light, can escape. The universe is full of these connections. Pull one thread and you find it attached to everything else. A companion star found in 2025 connects to a brightness cycle observed in the 1800s, connects to a dust cloud that dimmed the star in 2019, connects to the physics of mass loss that determines whether the remnant is a neutron star or a black hole, that connects to the population of compact objects in the galaxy, that connects to the gravitational wave signals that detectors like LIGO measure when those compact objects merge billions of years later. Everything is connected. That's not a mystical statement. It's a physical one. The universe is the system. Every part affects every other part. And the more closely we look at any single object, the more connections we find radiating outward to every other object in existence. Betelgeuse is one star, but it is connected to everything. Let us return now, one last time, to Siwarha, to the small star spiraling inward through the atmosphere of a giant. Because there is something about the way this story ends, or rather, the way it does not end, that deserves to sit with you as you settle in for the night. We do not know when Betelgeuse will explode. We do not know whether Siwarha will reach the core first. We do not know what the supernova will look like beyond broad estimates. We do not know whether the remnant will be a neutron star or a black hole. We do not know whether Siwarha will survive the explosion, be destroyed by it, or be flung out of the system at hypervelocity. Well, we do not know if the wake we detected is responsible for the Great Dimming. We do not know how many other red supergiants harbour hidden companions. What we do know is that we are watching. For the first time in the history of our species, we have the tools, the telescopes, the understanding and the patience to follow this story in real time. Not retrospectively, after the supernova has already happened and all we can do is examine the wreckage. but now while the star is still alive. Yes, while the companion is still orbiting, while the wake is still being carved, while the clock is still ticking. In November 2027, Siwarha will re-emerge to maximum separation. The James Webb Space Telescope will be watching. Hubble will be watching. The Gemini telescope with its Alapaca camera will be watching. New extremely large telescopes, currently under construction on mountaintops in Chile and Hawaii, will come online in the late 2020s and early 2030s with resolution sufficient to image the wake directly. We will see for the first time the trail of compressed gas being carved through the atmosphere of a dying star by its hidden companion. And beyond 2027, the observations will continue. Orbit after orbit, cycle after cycle, the data will accumulate, the models will improve, and slowly, carefully, painstakingly, we will assemble the most complete portrait ever created of a star in the final stages of its life. A portrait that includes, for the first time, the influence of a companion that was hidden for a century. It is a portrait that will not be finished in our lifetimes. Betelgeuse has tens of thousands of years left at minimum. The spiral of Siwarha will take thousands of orbits to complete. The supernova, when it comes, will come on its own schedule, indifferent to our curiosity, and indifferent to our impatience. The universe does not care that we want to see the ending. It will deliver the ending when it is ready. And perhaps that is the deepest lesson Betelgeuse has to offer. Not a lesson about nuclear physics or stellar evolution or companion stars. A lesson about patience. About the willingness to ask a question knowing that the answer will outlive you. About the extraordinary human impulse to watch, to measure, to record, to try to understand, and even when the full picture is centuries or millennia beyond your reach. The astronomers who first noticed the long secondary period in the 1800s did not live to see it explained. The scientists who hypothesized a companion star in the mid-20th century did not live to see it confirmed. Andrea Dupree, who has spent decades watching Betelgeuse with Hubble, will not live to see the supernova. The graduate students who will operate the Uranus orbiter when it arrives in the 2040s are in primary school right now, and even they will not see Betelgeuse explode. But each of them contributes a piece. Each observation, each measurement, each paper, each hypothesis adds a layer to our understanding. And the understanding accumulates across generations, across centuries, building toward a picture that no single lifetime could complete. That is what science is, not a collection of answers, and a collection of carefully constructed, continuously improving questions, asked by people who know they will not live to hear the final answer, asked anyway, because the asking itself has value, because the universe deserves to be understood, even if the understanding takes longer than any one of us is given. Betelgeuse has been there for 10 million years. It will be there for at least a few thousand more. The light arriving at your eyes tonight left before the Renaissance, and the light that will arrive on the night of the supernova left centuries or millennia ago. The universe operates on timescales that dwarf everything we have ever built, everything we have ever known, everything we have ever been. And yet, in the face of that incomprehensible scale, a species on a small rocky planet 650 light-years away looked up, noticed a red star on the shoulder of a hunter, gave it a name, watched it for centuries, detected its heartbeat, survived its sneeze, found its hidden companion, mapped its wake, and began to unravel the story of its death. That is not nothing. In a universe this vast, this ancient, this indifferent, the act of paying attention is an extraordinary thing. There is a thought experiment that astronomers sometimes indulge in, usually late at night, usually after a long session at the telescope, when the boundary between professional analysis and personal wonder becomes thin. The thought experiment goes like this. What will Orion look like after Betelgeuse is gone? Not during the supernova. During the supernova, Orion will be spectacular, transformed, dominated by a single point of light brighter than the full moon, where a modest red star used to be. That version of Orion will be a once-in-a-civilization sight, and anyone alive to see it will remember it for the rest of their lives. But after the supernova fades, after the months of visible brilliance dim to a faint glow, and the glow dims further, and eventually the point of light disappears entirely, leaving only a neutron star too faint to see with the naked eye and an expanding nebula too diffuse to notice without a telescope. What then? Orion will still be there. The belt stars will still form their perfect line. Rigel, the blue supergiant at the hunter's right foot, will still blaze blue-white. Bellatrix, the star at the right shoulder, will still mark its position. Scythe, the left foot, will still anchor the figure, but the left shoulder will be empty. The place where Betelgeuse burned for as long as anyone can remember will be dark. Not missing entirely because there will still be faint stars in that region. But the bright red distinctive star that gave the constellation its character will be gone. Orion will look lopsided, incomplete, like a portrait with one eye missing. Every culture that uses Orion for navigation, for storytelling, for marking the seasons, it will need to adjust. The hunter will have lost his shoulder, the figure will be recognizable but damaged, changed forever. And over thousands of years, as the expansion of the supernova remnant pushes the debris outward, the region around where Betelgeuse used to be will develop a faint, diffuse glow, visible only through telescopes. A nebula, a ghost. The scattered remains of a star that burned for 10 million years and then died in a few seconds. The future astronomers will study this remnant and reconstruct from the distribution of elements and the velocity of the expanding gas the history of the star that produced it. They will find anomalies in the remnant, regions of unusual density or composition, and they will trace those anomalies back to the influence of a companion star that orbited inside the atmosphere of the giant. Siwarha's fingerprints preserved in the wreckage are readable for tens of thousands of years after both stars have ceased to exist as recognizable objects. It is strange to think about the absence of something that has been present for all of human history. Betelgeuse has been in Orion for every generation of humans that has ever lived. Every baby that has ever been held up to look at the stars has had Betelgeuse in their sky. Every sailor who has ever used Orion to navigate has relied on the red star to mark the figure. Every astronomer who has ever mapped the winter sky has included it. The star has been a constant, a fixture, one of the few things in human experience that has genuinely never changed across the entire span of recorded history. And one day it will be gone, not in our lifetimes, almost certainly, not in our children's lifetimes or their children's, but someday. On some clear night in some future century or millennium, the light from the supernova will arrive, and from that night forward, Orion will never look the same. This is the strange melancholy of studying dying stars. You come to know them intimately, you track their heartbeats, their eruptions, their cycles, you discover their companions, you map their atmospheres, you model their cores, and through all of that work, all of that attention, all of that accumulated understanding, you are building toward a conclusion that is inevitable. The star will die, everything you have studied will be destroyed. The companion will be consumed or flung away. The atmosphere will be torn apart. The core will collapse into something unrecognizable, and the sky will have a hole where something beautiful used to be. But that melancholy is not the whole story, because the destruction is also a creation. The supernova is also a seeding. The death is also a birth of new elements, new nebulae, new molecular clouds, new stars, new planets, new possibilities. The atoms that are locked inside Betelgeuse right now and inaccessible, trapped in the body of a star, will be released, scattered across light years of space, made available for the next generation of everything. In a very real sense, Betelgeuse's death is a gift to the future, a dispersal of concentrated material into a universe that needs those materials to build new things. Without supernovae, the universe would be nothing but hydrogen and helium. No carbon, no oxygen, no iron, no calcium, no planets, no water, no life. And every complex thing that exists in the universe exists because a star died and scattered its elements. Betelgeuse will add to that legacy. Its death will be one more contribution to the ongoing project of cosmic construction that has been running since the first stars died billions of years ago, and that will continue running for billions of years to come. And Siwarha, whatever its fate, is part of that contribution, whether it is consumed in the explosion, flung away as a hypervelocity star, and or captured into orbit around a neutron star. Its story does not end with Betelgeuse's death. It continues, transformed, possibly damaged, certainly changed, but continuing. A survivor or a casualty, but either way, a participant in the next chapter of a story that has been unfolding since the universe began. There is a comfort in that, if you look for it. Not a human comfort. Not a warm, reassuring, everything will be fine kind of comfort, but a deeper kind, a cosmological kind, that the comfort of knowing that nothing is wasted, that every atom persists, that destruction and creation are the same process, viewed from different angles, that the universe, for all its violence and indifference, is remarkably good at recycling. Betelgeuse will die, its atoms will become something new, and the story will continue, with or without observers, for as long as the universe has energy to spend. That is enough. That is more than enough. That is everything. And let us go back to the sky, one more time, one last time, because there is something waiting for you there, if you choose to look. The constellation Orion is visible in the evening sky from roughly October through April in the northern hemisphere, and from roughly May through September in the southern hemisphere, where it appears upside down, the hunter standing on his head, perspective that Aboriginal Australians have been familiar with for 60,000 years, right now in March. And Orion is visible in the western sky after sunset, sliding toward the horizon as the winter constellations give way to spring. It will not be visible for much longer this season. In a few weeks it will disappear below the horizon, hidden behind the glare of the sun until it re-emerges in the pre-dawn sky in late summer. If you want to see Betelgeuse tonight, this is one of your last chances before it disappears for the season. Go outside, find the 3 belt stars, look up and to the left. At the red one, that is the star we have been talking about for the last 3 hours. That is the star with a companion spiralling through its atmosphere. That is the star that sneezed in 2019 and terrified the world. That is the star that will one day explode and transform the night sky forever. That is the star whose atoms will become part of future worlds. And right now, in this moment, it is just a light, a small red point in a vast black sky. Patient, steady, burning, waiting. And it has been there for all of human history. It will be there tomorrow night, but not forever. Where are you listening from tonight? Wherever you are, whatever time it is, the stars above you are the same stars that have always been there. Patient, enduring, indifferent to human timescales, but available to anyone who takes a moment to look. The universe does not hurry. Neither should you. The stars are patient. They will be there tomorrow night and the night after that. And for 100,000 nights to come. There is no rush. Rest now. And when you look up next, you will notice something about that red star that almost nobody else in the world knows. You will know its secret. You will know that it was never alone, and perhaps for a moment that will be enough. Sleep well. The universe is still here. And so is Betelgeuse, for now.